Your room can be dark enough to fall asleep in and still bright enough to delay your internal night. Your eyes call it dim. Your circadian system may read the same room differently. A bedside lamp, a bright hallway, and a nearby screen all send light toward your eyes. But the strangest part is that two people need not respond alike. In controlled tests, sensitivity to evening light differed by more than 50-fold. So the useful question is not whether your bedroom looks dark, it is what kind of evening signal your body clock actually receives. Tonight, we will reconstruct that signal, test the obvious light leaks, and find the limit the research cannot give you. First, a boundary. Melatonin is not the same thing as sleep. It is a marker researchers use to track the timing of internal night. These studies test timing under specific conditions, not whether one charger ruins everyone's sleep. One of the clearest experiments began with 116 healthy adults between 18 and 30 years old. For the main comparison, researchers examined melatonin profiles from 104 participants. On one visit, people spent 8 hours before bedtime in ordinary room light. On another, they spent that window in very dim light. The room light condition was below 200 lux, with typical eye level readings around 60 to 130 lux. The dim condition stayed below 3 lux. Researchers sampled melatonin repeatedly instead of asking whether the room felt bright. The difference was not subtle. Under room light, average melatonin onset occurred only 23 minutes before scheduled sleep. Under dim light, it occurred 1 hour and 57 minutes before sleep. That is a shift of roughly 94 minutes inside this experimental schedule. The measured duration of the melatonin signal was also about 92 minutes shorter in room light. And 103 of 104 participants showed an earlier onset in dim light than in room light. Those numbers are powerful, but they are not a personal brightness prescription. The participants were young, the schedule was controlled, and the exposure lasted 8 hours. Why can a room that feels dim still matter biologically? Because light entering the eye does more than create vision. It also supplies timing information to the circadian system. That system helps coordinate the daily rise and fall of melatonin. Light in the biological evening can delay that rise and suppress part of the signal. And the circadian response does not weight every wavelength exactly as ordinary visual brightness does. Researchers therefore distinguish photopic illuminance, related to visual brightness, from melanopic illuminance, related to melanopsin stimulation. That distinction is useful, but it still does not turn a single meter reading into a diagnosis. Now, zoom out from the eye to the room. For most of human history, electric ceiling lights, televisions, and phones did not extend evening on command. That does not mean every ancestor lived in perfect darkness. Fire, moonlight, candles, oil lamps, season, and place created very different nights. The important contrast is control. Modern rooms can hold a steady artificial twilight for hours from several directions until the moment we close our eyes. A natural sunset usually moves through its brightest to dimmest transition instead of waiting beside the bed. In one field comparison, the relevant sunset range passed in 22 minutes. Inside modern homes, the same biologically sensitive range can persist much longer. A 2020 study tried to measure that extended twilight where people actually lived. Participants wore a small spectrophotometer near eye level during normal evenings at home. The device recorded the visible spectrum every 2 minutes, not just a rough brightness impression. Across 59 homes, average melanopic illuminance during the 3 hours before bed ranged from 3.9 to 77.4 melanopic lux. That is roughly a 20-fold spread in the evening environment alone. The researchers then combined those home recordings with individual laboratory dose-response curves. The resulting suppression values were predictions, not direct melatonin samples collected in every home. Averaged across sensitivity levels, 48% of homes were predicted to produce at least 50% melatonin suppression. But that average hides the most useful result. For 42 people with reliable individual curves, the light level linked to half maximal suppression ranged from 3.1 to 181 melanopic lux. That is the more than 50-fold difference from the opening. Put the most sensitive person into the study's average home and the predicted response was large. Put the least sensitive person into that same average home and the predicted response approached 0. Across those individual curves, the average home produced predictions ranging from 0 to 87% suppression. Same room, same light, radically different modeled signal. This is exactly why a universal bedroom number sounds more scientific than it is. Without measuring both the light and the person's sensitivity, precision quickly becomes false confidence. So what makes up the signal your clock receives? First is intensity at the eye, not merely the wattage printed on a bulb. Distance, angle, shade, reflection, and whether your face points toward the source all change that input. Second is spectrum. Two lights can look similarly bright while producing different melanopic values. Third is timing, because light near biological night is not equivalent to the same light at noon. Fourth is duration. An 8-hour laboratory exposure is not the same as a brief glance. Fifth is the person, including the large sensitivity differences the studies exposed. Brightness is therefore not one knob. It is a panel of controls, and most bedrooms leave several turned up at once. That gives us a better bedroom audit than staring at one lux number. Stand or sit where your eyes actually spend the last hour before sleep. List every source in your field of view: lamp, ceiling fixture, hallway, screen, charger, clock, and window. Now separate the sources instead of judging the room all at once. Turn off one source, return to the same position, and notice what changes at eye level. Then repeat, keeping the time and viewing position as consistent as possible. A phone light meter app can help compare your own before and after setup, but it is not a calibrated spectrophotometer. Use it as a relative comparison, not a medical threshold. There are 4 traps this audit should avoid. Trap 1 is treating melatonin as a direct score for how well you will sleep tonight. The home study found that brighter than usual evenings for a given person were associated with more wakefulness during the first 90 minutes after bedtime. That association does not prove that light alone caused every restless minute. Trap 2 is declaring all LEDs bad. In this sample, evenings dominated by LED or fluorescent light had higher average melanopic illuminance than incandescent-dominated evenings. But each category covered a wide range, and placement and intensity still mattered. Trap 3 is assuming a warm-looking lamp is automatically harmless. Spectrum matters, but so do intensity, distance, direction, timing, duration, and sensitivity. Trap 4 is copying someone else's safe number as if their eyes, schedule, and biology were yours. The studies themselves argue against that shortcut. A more honest test changes one variable at a time. Night 1 can be your ordinary room. On another comparable evening, remove the single source that shines most directly toward your eyes. Keep your intended bedtime and the rest of the setup as stable as real life allows. You are not running a clinical trial or diagnosing a disorder. You are identifying which design choice creates the largest controllable difference in your room. For one person, it may be a ceiling fixture aimed downward but reflected across pale walls. For another, it may be a lamp placed beside the face. For someone else, the dominant input may be a bright screen used close to the eyes. The point is not to fear every photon. It is to find the source doing the most unnecessary work. Once you find it, solve the geometry before buying a new gadget. Block the hallway gap, lower the lamp, turn the shade away, or move the screen farther from your face. Reduce the amount of light reaching the eye during the final part of your evening, when practical. If you change the bulb, compare spectrum and output instead of trusting color names alone. And preserve enough light for safe movement. Darkness is not a contest. No single change guarantees faster sleep because the research does not isolate your bedroom, sensitivity, habits, and health. The defensible goal is smaller. Remove avoidable evening light and make the night signal clearer. We can now answer the question hidden inside the title. Your bedroom may be too bright for your circadian system, even when it looks comfortable to your conscious vision. That mismatch exists because visual comfort and biological timing are related but not identical measurements. The signal depends on how much light reaches the eye, its spectrum, its timing, and its duration. Then individual sensitivity can multiply the difference. That is why the research gives us strong evidence for the problem, but no universal bedroom cutoff. The useful measurement is not one magical number. It is a map of sources, geometry, timing, and uncertainty. When you remove the largest unnecessary input, you are not recreating prehistory. You are simply making electric evening easier to distinguish from night. And when the final light disappears, another strange thing often happens. The room can suddenly feel louder. A refrigerator hum, distant traffic, or your own breathing moves forward because the visual scene has become quieter. That is not the same mechanism as melatonin, and it deserves its own evidence. So next, we will ask why silence seems louder at night and what your brain is actually turning up. For tonight, start with the room your clock sees, not only the room your eyes call dark.